So now we're going to cover an application of transformer EMF and the dynamic version of Faraday's law, right? So the application here is exactly as the name is, transformer EMF. It's just transformer. So this is one of the most common applications of this law, and it's a device that has revolutionized the way that we transmit power from one place to another place. Okay, so what happens in a transformer? How does a transformer work? So what we're going to look at is the ideal case of the transformer. The real case of the transformer has a couple more nonlinear phenomena that we have to consider, and it's a trickier model. And if anyone's interested in that, I cover that in detail in my electric machinery class. But in this class, we'll simply go over the ideal case. So let's think what happens here. Well, if we have a voltage, right, and it passes through some solenoid there, right, which is one winding of the transformer, it's going to produce a magnetic flux. That magnetic flux is going to flow through the core like this, okay, and we'll call that B. All right, and that's, you know, the same magnetic flux that was produced in the magnetic circuit equations that we covered previously. Okay. So what we should notice here is that we have basically a magnetic circuit, okay? If we have a current which is going to flow here, which I'm going to tell you is going to happen because of the principal operation of a transformer, and we have a current that flows here, we're going to produce two MMFs. Let's say that we have N1 turns in that solenoid and N2 turns in that solenoid. We can then develop an equation, right, that would say the total MMF is going to be basically the difference of the two, right? The difference of the two. So we would say N1 I1 minus N2 I2. And the reason why we say minus is because you can see that in this, the way we denote it here, we have the current I1 is flowing into the solenoid, but current I2 is flowing out of the solenoid. So this is just telling you the directions, okay? Well, the difference between those two, basically using Ohm's law for magnetic circuits, is going to be equal to the reluctance of that core times the flux which flows through it. Okay, now in the ideal case, we're going to say that this is an ideal core or an ideal transformer. What does that mean? Well, in the ideal case, this means that the permeability of the core goes to infinity, right? So it means we have infinite permeability. When we have infinite permeability, that would mean that all the fluxes confine to the core and none will actually leak out. In actuality, in a real transformer, you'll have flux that will leak out and it won't link the other winding, okay? But we're just going to consider the ideal case for the time being. Okay, so if the permeability here goes to infinity, this means that the reluctance of the core, which is inversely proportional to the permeability, is going to go to 0, right? So that means we're going to have no reluctance, right? If we have no reluctance, that means this term right here is going to be equal to 0, right? So that means the MMF from winding 1 minus the MMF from winding 2 is equal to 0, okay? That's how we're going to get our first equation for the relationship of currents and turns in a transformer, and we'll get N1 I1 is equal to N2 I2. Okay, that's how we relate the currents in an ideal transformer. Okay, how can we relate those voltages? Well, the way we can relate the voltages, let's fall back on Faraday's law. And what I'm going to do here is I'm going to ignore the negative sign for Lenz's law, because we know that we'll just have a positive polarity build up in the way that it is there, and we'll just omit the negative sign. Okay, so we'll say that V1 is going to be equal to the rate of change of flux linkage with respect to time. Okay, well, the flux linkage here, I'll put flux linkage 1 because it's different than 2 because we have different turns. So this is going to be equal to N1 times the rate of change of flux with respect to time. Okay, So that's the flux linkage in winding 1. Well, V2 is going to be equal to d lambda 2 d2 dt, and this is going to be N2 times the rate of change of flux with respect to time. All right, so we have two different equations here, one for V1 and one for V2, but you can see that we have one common term in both equations, and that is the rate of change of flux with respect to time. And if this is an ideal transformer, that means that the only flux in the core is going to be the one that links both windings, right? So that's one common flux, and there is no other flux. So from this point, we can set these two equations equal to each other, right, by dividing N1 here. So we'd say V1 over N1 is going to be equal to the rate of change of flux with respect to time, right? But if we divided this side of the equation by N2 and this side of the equation by N2, we'd have the exact same equation, except we'd relate V2 to N2, okay? So from here, we have derived our second relationship relating the voltages in a transformer, which is ideal. It's important that we say ideal. And it's V1 divided by N1 is equal to V2 divided by N2, okay? Let's do a quick example to apply this. In this example, for this exact transformer right here, let's say if N1 is equal to 40 turns, assuming ideal, how many turns for N2 would double the voltage V1 at winding 2. Okay, so sometimes when we're talking about transformers, we'll consider one winding, let's say this one, V1 to be the primary, and V2 here would be the secondary. So we could say winding 2 or the secondary winding. Winding 1 or the primary winding. Sometimes we'll also say high side and low side, depending on how the transformer is configured. So basically, here's what we have. We have 40 turns here. We want to get a voltage out here, which is twice that voltage right there, right? So we want to double the voltage on the secondary side. So how would we do that? Well, let's just look at our equation right here. V1 over N1 is equal to V2 over N2. Well, we know that V2 should be twice V1. So V2 is equal to 2 times V1. Replacing that, V1 over N1 is equal to 2V1 over N2. Okay, these V1s will just cancel out, so you see it's independent of the actual voltage. And then we're going to say that N2 should be equal to 2 times N1. Well, we know that N1 is equal to 40 turns from the problem statement. So from there, we can see that N2 should be equal to 2 times 40 turns, or 80 turns. Okay? So if we had 80 turns on the secondary and 40 on the primary, we would get double the voltage out on the secondary than on the primary. One thing that's interesting to note here is that we always have to have conservation of energy, right? So that means that energy can't be created or destroyed. So if you think about this, we can always relate energy to power, okay? So what is the power that's input on this winding? Well, that's going to be V1 times I1, right? Well, if we are going to conserve energy and conserve power, we have to have the same power output on this winding that was input on this winding. So that means that if we double the voltage, we have to at the same time cut the current in half, right? So if we double the voltage and cut the current in half, when we multiply the voltage times the current, we'll have the same output power as we had the input power. And let's check, would that really happen? Well, if we look at this current equation, which is this guy right here, we would say Well, N1 is equal to 40, right, times I1, okay? And then N2 is equal to 80, so at 80 I2. So could we get I1 as a function of I2? We would say, well, I2 is going to be equal to 40 divided by 80 times I1, or 1/2 I1, right? So we said that V2 is equal to 2 times V1, and I2 is equal to 1/2 I1. Now what happens when we multiply I2 times V2, which would give us P2? Well, that would give us 1/2 I1, right, for I2, multiplied by 2 V1 for V2. These two are going to cancel each other out, and what do we get? I1 times V1. So you should see that the output power is exactly equal to the input power, and we have conservation of energy. Okay, just one quick caveat is that this is an ideal transformer, so actually we're going to get some power dissipated by these windings in a real transformer, right? These windings have some internal resistance, so we're not going to get exactly the same power here. We also have what's called hysteresis and eddy current losses through the core, so they'll also dissipate some power, right? So you're not going to get exactly the same output power, because you're going to get some of that power consumed by some of the parameters here. But none of those are considered in the ideal transformer. So in the ideal transformer, you should have output power is exactly equal to input power, or we could say the transformer is 100% efficient.